So today, we're going to talk about pipe flow again, and we're going to talk about minor losses. What does that mean? So what we've talked about so far, pressure loss or energy loss from friction, that's also known as major losses, and that's because most of the time, most of the energy that gets lost in pipe flow is going to come from friction on the walls of the pipe, like we've been talking about. Okay, that's why that's major losses. But you also get energy lost in other ways. Things like valves in the flow. If flowing around a valve, energy will be lost. Expansion, so if you have, say, a narrow pipe and it expands into a bigger one. Contractions, the opposite. Entrances, so flowing from a pipe into a tank, that's an entrance. Or exits, bends or curves in the pipe. Branches, where the pipe branches out. All of those things, in all of those places, you will get energy lost. And the way we estimate the amount of energy that's lost, so that we can put it into our mechanical energy balance and do our problems, is through something called a loss coefficient. So this is something that would need to be experimentally measured. And what you do is, okay, so you have something, a bend, a fitting, a valve, whatever, and there's a certain amount of head loss associated with this. Just would someone please remind the class what head loss is?
The height that's lost when, basically it's the loss of height in the energy formula.
Okay, the loss of height, but that the height there is it really height necessarily, or could it also?
It's another way of writing energy?
Yeah, it's another way of writing the energy that's lost or the pressure that's lost. So yesterday we talked about delta PL, and all the problems we did were in pressure drop, pressure loss. So how do you get from pressure loss to head loss?
Divide by rho g.
Yes, Rinkin, you divide by rho g. So it's another way of saying the pressure that's lost to friction, or the pressure that's lost as energy is lost. Another way of representing that, just as a reminder. Okay, so for every fitting or valve or something, there will be a certain amount of head loss. And we want to make a dimensionless loss coefficient. Okay, so what could we divide head by? Head is in units of length, so what could we divide it by in order to get something dimensionless?
Diameter.
Okay, diameter, but the diameter doesn't really have a big effect on how much energy is lost. So how much energy is lost is going to come more out of, that is a good idea, and that is how we non-dimensionalize units of things with length a lot of the time. In this case, we're not going to do that because what we want is something that relates to the velocity and the kinetic energy, because the faster the fluid is flowing, generally the more energy will be lost as it's going around all of these little obstructions and obstacles. So we do it like this. So this is the kinetic energy term from the mechanical energy balance. So if we did the head form of the mechanical energy balance like this, okay, so this would be the head form of kinetic energy. So that's what we are going to non-dimensionalize this head loss with. And the reason, as I said, we do this is because how much energy is lost is going to depend on how fast the water is flowing, how much kinetic energy there is there. Okay. So that's the loss coefficient. And the loss coefficient needs to be experimentally measured. So you would run fluid through a bunch of these things, measure the head loss over that valve or whatever, and then define a loss coefficient. Okay, so if you wanted a very accurate loss coefficient for your very specific valve you have in your plant, you could experimentally measure it yourself, or you could look up standard ones. There is a table in your book in chapter 8 with loss coefficients for various common fixtures. And of course, you could also find them online in Engineering Toolbox or in Terry's Handbook. There are lots of places where you could find standard literature values for loss coefficients for different things.
So I'm assuming that with a valve, the loss coefficient depends on how far down it's
Yes,
tilted.
so partially open valves are gonna be some, it depends on how accurate you want to be. So a lot of tables will give you like something for a half open, a quarter open, or 3/4 open something valve, or maybe they'll just do half open or full open. And a lot of times that'll be close enough for your purposes. If you need to be more specific, you would need to be more specific, either by measuring it yourself or by finding somewhere in the scientific literature some more specific correlation.
Okay.
All right, and so then you have this additional head loss term, or this term for the head loss caused by your dude. I believe table 8.4 is the table in your book we were talking about. Okay. So let's talk a little bit about where this loss came from, and these losses come from, and one of the best ways to illustrate this is by talking about entrances and exits. So a lot of times you'll have, say, a tank, and then it'll go into a pipe, and then it'll go out of the pipe into another tank, stuff like that. That's what we mean by entrances and exits. So if we look at this table, table 8.4 in your book, you should see that, there we go. You should see this. A sharp-edged inlet into a pipe has a loss coefficient of 0.5, whereas a rounded inlet has a loss coefficient of 0.03. So that means you get a lot more energy loss around a sharp-edged inlet than you do around a rounded one. Rounding the corners reduces your energy loss. Does someone have an idea of why that might be?
Well, looking at the picture, is it because of flow separation?
Yes, Avonlea. That is exactly what I actually did not expect any of you to say those exact words, but yes, that is exactly why. So the sharp edge, yeah, and it's just like the rounded one is kind of streamlined, right? But just like we talked about. Okay, so the sharp edge one has more flow separation. And this creates these eddies here, right? And those eddies are called vena contracta. And essentially it's this place where instead of flowing forward, the flow is just swirling around, shedding energy, spending energy, swirling about, and you're going to get more loss. And in fact, the losses in all of these minor losses, they're caused in part by interruption of the flow, which creates eddies and vena contracta and little turbulent wakes, like we talked about with drag. And that is where the energy is going. Okay, so things that are more smooth will tend to have less energy loss. The same thing with, say, bends in a pipe or a duct. A smooth, rounded bend is going to create less energy loss than a sharp 90-degree bend. And you can reduce energy loss in these bends by adding in these little veins that sort of streamline the curve and help the flow go. The vena contracta, it's just these sort of swirling eddies inside the flow. I don't know what vena means in Latin, but contracta, I assume, has something to do with contraction and becoming this. These eddies also kind of squeeze the flow in. They contract it, so you'll also get some energy loss there. Okay, so then we can combine major and minor losses. So we got, say, a head loss from a pipe. This is the major loss from friction, and the head loss from each fitting or thing inside of it. And then you put them together, and you have here. This is another reason it's useful to measure the loss coefficient so it scales with this kinetic energy term, because we also know that the major losses scale with this kinetic energy, and you can then put them together like this. So Nicholas asks, can we consider KL to be the amount lost per the kinetic energy of the pipe at that point? Yeah, sort of. Because it's just scaling the amount lost with the total kinetic energy of the pipe. You could say that. Okay. And yes, this would be for a pipe of constant diameter, though, again, if you look at the losses, it will allow you to figure out if there's a section that's like this, where it starts narrow and gets wide, you can use a loss coefficient to figure out what the pressure drop or the head loss over that will be. Okay. We will also talk on Friday about what happens if you, say, have a small pipe and then it flows into a big pipe, and how you would solve a problem like that.
I have a question.
I also have Tyler saying, does this work only for turbulent flow? So it's just like the drag coefficients, where what you need is you can use these coefficients only in the situations they were measured under, and generally they're characterized in turbulent flow. I have not done problems with minor losses with laminar flow, though also with laminar flow, it's slower. It's more viscous, so that the flow is going to be more able to just sort of curve around these obstructions. And so the minor losses in laminar flow would be much lower. There may be some applications where you would need a way to characterize minor losses in laminar flow. I've never done that. You would need to find out how that was done, but it usually will not be as big a problem. If the diameter is changing, which d do you use in the equation? Asks CJ. So that will depend on, well, let's see. I want to show you. Let me actually bring up the chart. It'll be easier to talk about then. Okay, so, excuse me as I stop sharing. Where is, okay, here we go. Now I'm just going to share the screen. All right, here's the table. Easier to talk about here. So if, for example, right here, okay, the chart actually tells you which diameter it wants you to use. So for all of these, the inlets and the exits, you're using the diameter of the pipe, not of the big tank. And you're just kind of assuming the diameter in the tank is so big, it's almost infinitely big compared to the diameter of your pipe. And then for something like this, which is an expansion or a contraction, there's a little d of the small pipe and a big D of the big pipe, and the loss coefficient actually has both of them in it. Okay, and so then for which diameter you would use in this part? Well, you would use, if you were doing some problem, there would be a separate head loss for the long stretch of the small pipe, and then another one for the long stretch of the big pipe, and then there would be a minor loss for in between them that would use both of the diameters like that. And again, we will do more problems like that on Friday. Now, going back to this. Okay, so we're going to do a problem here. And actually, we went through this pretty fast. We might leave earlier today than I thought, though we can just stay and talk about things if you want. But first, let's do this problem. Do we have any questions about anything we've talked about so far before we get to the problem?
I'm trying to figure this out in the chat and I'm still a little confused.
Okay.
So in the Bernoulli equation, when we calculate head loss, is that including the minor head loss as well? Or only
yes. So you say the Bernoulli equation, though, usually when we say Bernoulli equation, we mean the version that doesn't have any head losses or any pump or turbine head. Okay, so we mean the version that doesn't have any losses. That's what we usually mean when we say Bernoulli equation. Though it's not wrong to say that the whole thing is the Bernoulli equation. People call this okay, you can also call this the engineering Bernoulli equation. That's something people call that. So that was just an aside. Second, to actually answer your question, this would be the total head loss. So for example, in this problem, we're going to go from 0.1 over here to 0.2 over here. And so the head loss we would put in our balance would be the total head loss, including the major losses from the friction in the pipe and the minor losses from all of the little stuffs.
Gotcha, thank you.
So here we have water at 10 degrees C, and I have shown you, I just went ahead and gave you the properties here. Water properties, especially the farther away, the water properties you just kind of have in your head when you're assuming, you know, density equals 1,000 kilograms per meter cubed, viscosity is equal to 0.001 kilograms per meter second. The farther away you get from 20 degrees C, the worse error you'll get from just assuming that. Because at 20 C, it's like 998 kilograms per meter cube. Anyway, so we have 10 degrees C, it's a little colder. We look up our properties right there. And now it's flowing from here to here. And what we are trying to find is what depth of water here will result in a flow rate of 6 liters per second through this system. All right, so hopefully as soon as I put this up, you started thinking about how you were going to set this up. Does someone want to tell me how they started, like the first thing they did?
The first thing that I did was I canceled out the delta P term and I canceled out the delta V squared term.
So the first thing you did is you wrote out the mechanical energy balance like this, and you canceled out delta P Why were you able to do that?
Because the pressures are the same. They're both atmospheric pressure.
Mm-hmm. And then you also canceled out the delta V squared term. Why were you able to do that?
Because I think we're assuming that the tanks are so big that they're not dropping any.
Yes, so whenever tanks are big enough, the water in this will be dropping, but since the tank is so big, the water level is dropping so slowly, we will assume the velocity is 0. Okay. And here's that delta Z term, and this delta Z is what's going to ultimately give us our answer of what Z1 needs to be. There's one other thing that can cancel out in this equation. I'm going to call on someone. How about Carter? Carter, how are you?
Doing all right.
Doing all right, thank you. So Carter, there's one other term that can cancel out here. What do you think it is? Yeah, there's something that this setup does not have that just doesn't appear at all in here.
Pressure change?
Well, we already canceled out pressure change. We already canceled out pressure change and velocity change. There's one more thing that we can cancel out because there is something that does not show up here.
Is there no pump?
There is no pump.
Pump.
There's no pump or turbine. So there we go. So we actually end up with a pretty simple balance of just okay. And what this can translate to essentially is that the height here is going to provide enough potential energy, enough weight pushing down to push this fluid through the pipe and overcome all of the losses, all of the energy loss all along that pipe. Okay. So now let's take Sion.
Can you hear me?
Okay. So if we start here and we just write this out, what would you do next?
I could replace the head loss equation with the major plus minor loss.
Okay, you're gonna, sounds good to me. So delta Z is equal to negative head loss. It's equal to negative F L over D plus the sum of all the loss coefficients times V squared over 2G. Someone wants to check to make sure I didn't forget anything, but that should be good. Yeah, that should be good. Oh, by the way, just to note, a quick head check I just did in my head to make sure I wrote this out right, as I looked and I was like, okay, F over L over D, that's dimensionless, KL, that's dimensionless, V squared over G, that's gonna be length units, and so we're good. All right, and so then F, okay, so the sum of KL, what is that? We've got
0.5.
Yep, for the entrance plus
0.3
Plus-
times 2 plus
Yeah.
0.2 plus 1.06, which equals 1.37.
okay, And so I said 2 times 0.3 because there are 2 elbows here, and then plus 0.2. Then plus 1.06 for the exit. So you'll notice the exit is actually the biggest loss here. And you will also recall that in a lot of the problems we did where we just neglected minor losses, we didn't include any of this, even though they had exits and entrances into things. And so there's a little bit of error that happens every time you ignore the loss from these entrances and exits. That's just something to keep in mind. And the more bends and things that you have, the bigger error you'll have from ignoring or neglecting minor losses. So by the way, I actually had a student in my 391 class give a presentation on a project she did for her internship. So it was for, I think, GE, so it was a big company. And after coronavirus, all the workers had to wear masks. And so they wanted to improve the ventilation on their factory floor, both because improving ventilation is good for preventing viruses from spreading anyway, but also because that makes it more comfortable for people wearing masks. And her project was to find out why some places in the factory had worse ventilation than others. And what she found was that in some of the places, the air ducts that recycled the air had all of these 90-degree bends in them. Okay, so more of these 90-degree bends in the air ducts meant more head loss, more pressure loss. Okay, and so this led to worse airflow because the more energy loss you have, then the same amount of pumping or fan power will get you a smaller flow rate. So that is an example of this coming up in a real world application. Okay. Alrighty, so that's that. 1.1, 2.36. Okay, and then how will we get F?
Well, if we want to do it the easy way, we could take 1 over the square root of f equals to negative 1.8 log base 10, 6.9 divided by the Reynolds number, or just use the Holland's equation.
Yes, we want to use one of those. We need to do it the same way we did yesterday. So either the Holland equation or the Colebrook. Right now, let's use the Holland so we don't have to do any fancy iteration. The thing I would do first is find my Reynolds number. So this is 6 liters per second. So, which is the same as 0.006 meters cubed per second. Velocity would then be v dot over pi over 4 d squared, and we would want to use the d for this pipe because we want the velocity in the pipe. That's what is going to give rise to our losses, and it is 5 centimeters. So will someone tell me what you got for the velocity?
3.055 or 3.05. Oh, 3.06, sorry.
3.16, you said?
3.06.
3.06 meters per second. Okay, then we put that in the Reynolds number. That'll be rho v d over mu. And our rho is 999.7. Our v we just found was 3.06. Our diameter, 0.05 meters. And our viscosity is 1.307. 10 to the negative third. kilograms per meter second. Will someone tell me the Reynolds number you got?
I got 117,027.
123.
117.
27.
117,000.
117,000.
Yeah.
Sorry. Okay. And so it is turbulent. So if it were laminar, again, we would want to use F is equal to 64 over the Reynolds number. But since it's turbulent, well, we're going to use either the Holland or the Colebrook equation. I'm going to use the Holland so we can just do it here in class. So 1 over square root of F is equal to which if I were to just solve for F,
What was the material again?
the material is cast iron. So a question for somebody else, why did he want to know what the material was? Sarah, maybe? Sarah Ahmad? Let me know. Everyone tell me if I pronounce your name wrong, by the way. Sorry.
Oh, no, you pronounced it right.
Okay, thanks.
To find the epsilon thing.
Yeah, to find the epsilon thing. The epsilon thing is the roughness, so that's why you need material. So somebody, what was epsilon for cast iron? Someone look that up?
I got 0.26 millimeters.
0.26, did you say?
Yeah, 0.26.
Okay, 0.26 millimeters. And that looks about right to me because it's on the high end for these roughness factors. And I would expect iron to be on the highest end compared to like plastic or even like stainless steel or something. So that makes sense to me. So this will be the big plug and chug. So I want at least a couple people to tell me what they got for F because it's pretty easy to make some little plugging in error here. So I want to, let's have people put it in the chat because I want a couple, I want it to, someone to second it. Okay. Okay, I got 0.035 from Zach and from Sarah. So 0.0315. All right, this is again on the slightly highish end of friction factors. And again, this makes sense to me since cast iron is going to be rougher and have more friction than a lot of things.
Dr. Nickerson.
Yes.
What's the exponent on the second part in the equation?
This is a -2. That does look weird just because.
No, the one inside of the.
Oh, that's 1.11.
Okay.
Okay, so now we have F. And so delta Z is equal to negative head loss equal to negative, let's see, 0.0315, that's F, times the length of this. So let's see. All right, so what length are we going to use here? This is a question that you're going to have to figure out from looking at that figure I gave you.
89?
89. Yes, it is 89. Why is it 89 and not 80?
Because it goes across 80, but it also goes down 9.
Yep.
So you have to add the lengths together to get the total length.
That's exactly right. Because this length tells you the length that the fluid is flowing through and rubbing against the wall, which is where that friction loss happens. So you need the whole length of the pipe, not just sort of not the delta X, ignoring the way it sneaks around. Okay. Plus. So again, in the chat, put what we have. Got 3.33. And what would the units on that be? From Connor, what would meters? Okay, is someone, let's see if someone seconds Connor. Oh, sorry, negative. Negative is important.
I have a question.
Someone got 13.1 meters, Nicholas did. So I have 3.33 and I have 13.1. Let's see, let's get a few other votes. All right, what was your question?
So when we're doing doing the term back when we're finding the friction factor, the term that has the epsilon over d, if that's epsilon, do we have to get both of those into meters?
Well, so you always need to put things in units that match. So you could put them both into meters or you could put them both into millimeters. It doesn't matter. They just have to be the same units.
Okay, cool, thanks.
So Mara says 9 meters taking top vertical length. What about the length of the top horizontal part? This horizontal part plus this horizontal part becomes this whole length, and that's 80 meters.
I see, thank you.
Okay, so we have multiple people getting negative 27.9. I do not remember what I got when I plugged this in. So for now, we'll take that on faith that that's right. Though, as I said, with these complicated things, you always want to double check because there's a lot of places where you can just plug something in wrong. So if delta Z is negative 27.9, what does Z1 have to be? $31.9 meters. Okay. And that's it. That's basically it. And mostly the problems, the way you set up problems doesn't change if there's minor losses. You do it exactly like all of the problems we learned about yesterday. And you would set up balances and solve problems and use solvers or whatever if you had to, just like all of those problems, except for now, for the head loss or the pressure loss term, we would add in the minor losses. Now on Friday, what we're going to do is, again, we're taking basically the same kind of problem and we'll just make it a little bit more complicated. On Friday, we'll do that by adding pipe networks. So for example, if it goes from one pipe into another pipe of a bigger diameter, or if it splits from one pipe into two pipes, things like that. That is what we will cover on Friday. Okay, and that is what we have for today. We actually ended early instead of late for once. Does anyone have questions about this or about yesterday's stuff or about anything?
Well, I think I went down a rabbit hole doing the second problem.
All right, I had
number 2 on the homework yesterday.
You are being kind of quiet. Do you speak up?
Can you hear me better now?
Oh yeah, that's better. Thank you.
Interesting. Okay. I had a bit of trouble on problem 2 on the homework from last night. Would you mind going over that?
Sure. I would love to look at that with y'all. Okay, so I'm gonna close out of this. Hopefully you all see this. Okay. We've all seen this. Now let's look at homework from last night. So that would be homework from last night. Do you mean homework 11 or homework 10? Like the stuff that was due yesterday or the stuff you started yesterday?
I'm pretty sure homework 11.
Homework 11.
Yeah, that's the one.
That is the one. Okay. Number 2. Okay, so number 2 is this guy. Okay. So first of all, what is the ultimate thing we're trying to find? What is this problem asking for?
It's asking us to solve for diameter.
For the diameter. Okay. So if we're trying to find diameter, what do we need to know? Or there's several things we need to know, but let's say we talked about different kinds of problems you would solve with this, right? And usually the things we're interested in are the diameter, the flow rate, and the pressure drop, yeah. So you need to know, so in order to find the diameter, we would need to know delta P and the flow rate, right? All right, so let's set up our mechanical energy. So do we know the flow rate here?
It'd be 15 gallons per minute.
15 gallons per minute. Perfect. Okay, and how about that delta P? How do we think we're gonna find that?
I'm pretty sure it's 14 psi.
Is it though? Is it? All right.
No.
So that is, I'm glad. Yes, so this is a good thing to repeat because it is very easy to look at this and think it's 14 psi, and the overall pressure difference will be 14 psi, but we want to find just the pressure loss from friction. So yes, you're right, the overall difference is 14 psi, but that is not all we need. So I'm going to set up a mechanical energy balance here. Okay, and to draw. Where should I put my 0.1?
At the top of the milk jug thing? Well, at the top of the tank?
Yeah, at the top of the tank, inside the tank somewhere, doesn't matter. just in the tank. And where should I put 0.2? Going into the jug. That was supposed to be jug. It looks bad. Anyway, 0.1 and 0.2. So P1 will be, P2 will be P atmosphere. And P1 would be 14 psi above P atmosphere, so just P atmosphere plus P 14 psi. What's Z1 and Z2?
Z1 is going to be the 5 feet, and then Z2 we can just set to be 0.
Mm-hmm. And what about V1 and V2?
Are they both 0?
Yeah, let's say it's about equal to 0. Okay, that's.
Don't you have fluid flowing along the
You,
entire?
in fact, I said about equal to 0. I'm not sure. It's definitely pretty much 0 up at the top, but at the bottom, as it's coming out, that's going to be whatever velocity is coming out. I might not cancel that out. It could end up being pretty small, so we could ignore it, but maybe it wouldn't. And so velocity would be whatever the velocity. And so you'd want to put V in there. We don't know what it is because.
Yeah, I worked through it twice. One with the assumption that they had the same velocity at both points, and then one where the first velocity was 0.
Yeah,
It only made a difference of like 0.3,
like
no, 0.03 inches.
Okay, so like 0.03. Yeah, that's going to be, normally you can't get pipes. They're at ½ inch intervals, so you wouldn't even be able to get a pipe that took that into account. So if you assume V2 is 0, you won't get that big of an error. But it would be more correct to keep it.
So does that mean that it's just going really slow through the?
Yeah, it's going slow, and also just the size of this term is going to be small compared to the size of these other ones. So this delta P, that's 14 psi. That's a full atmospheric pressure. That's pretty big. And then your losses are also going to be pretty big, your major losses that we've been talking about. Your delta Z is a whole 5 feet. That's probably fairly significant. And so just all these guys will probably be pretty big compared to what this is. So the velocity is small, by which we mean it's small enough that this term will be small compared to the other things.
So does that just mean that the pipe has to be wide enough to have 15 gallons per minute, even at a really small velocity?
Well, yeah, but yes, though I know it would have to. It might turn out one way or another. You can't necessarily say at the beginning, but I would say that in a lot of situations, the kinetic energy term will end up being small compared to the other ones.
Okay.
What
So
does
just
V
setting
affect
V2
in
equal to
this
0?
problem then, says Nicholas? Well, it affects the pressure loss. But yes, so it would be more correct to put this in. It's probably small. I might just go ahead and assume it's 0 at the beginning, just because from my experience, looking at the other numbers in here, I would expect it to end up small, but that isn't like a 100% certain thing that you should 100% count on.
For the energy balance, is that G supposed to be there in the velocity term?
In the velocity term, let me see. This is trying to be pressure. No, it's not. Thank you. Yeah,
So
rho v squared is pressure.
So on this one, if you were to not make that assumption that the velocities are the same at 0.1 and 0.2, then what else would, because I guess what I did, I picked my point just as it was entering the pipe, but I guess that would then make it that the pressure would be thrown off, because I was thinking that because it's going in and out that same pipe, then the diameter being the same in incompressible flow would mean that it has to be the same velocity,
So
but that might throw off the pressure.
Yeah, Spencer, that's probably right. Is that if you did that, if you set 0.1 like right inside there, the pressure would probably be a little different going out there. But as I said, it's such a small difference that it's kind of a choice about how you would decide that and where you would set it up exactly.
Because in the end, either way, you'd be getting the same answer. It would just be whether you're being thrown off because you're assuming the different thing with velocity, or because it's throwing off the pressure when it goes in. Because once it starts moving faster, so once it goes from kind of inside the pipe, or I guess inside the tank, to the point where it's starting to flow, then it's speeding up and its velocity would be higher, so its pressure would be lower.
Yeah.
So how would we do it if we don't make that assumption? Because it seems like if we don't make that assumption, then we would have too many unknowns.
Well, if you don't make that assumption, this problem is going to end up with a system of equations anyway, right? And V is one of your unknowns, so it would just be there in your equation. Okay, so I'm going to write this out as if we didn't make that assumption, though, as I said, I think when I did it, I just assumed it, but let's say you don't. Okay, and we would end up with something like a delta P loss is equal to negative delta P minus 1/2 rho. I'm going to assume alpha is about 1 because we're going to assume turbulent flow. Kinetic factor is 1. And so that's just going to be V2 squared minus rho G delta Z. Okay, so that's one equation. And then what's our second equation going to be?
The Colebrook equation.
Yeah, well, the Colebrook equation will come in eventually. I wanted to start with this one. B squared, like that. Okay, so now let's do the Colebrook equation as that's 2. And when we're using the Colebrook equation, we are assuming turbulent flow. That means that after we find whatever our diameter is, we want to go back and calculate the Reynolds number to make sure our assumption was good. Okay? And if at the end we calculate our Reynolds number and it's like 500 or something, we would say, okay, that wasn't a good assumption, and we'd want to go back and do it assuming it's laminar. Okay. Whatever. The Reynolds number's in here. Whatever that is.
Did you write 2.0 or 20?
1.8 was for the Holland, 2.0 is for the Colebrook. Then there's some other numbers that I can't remember which it is for which. So I just put some squiggles there. Okay. And then Reynolds number would be rho V D over mu. And I'm writing these out. I'm listing it as 4 equations, but you can always say, plug that Reynolds number equation into there. Actually, let's list this as 5. Okay, as I said, I'm listing this out as 5 equations, but you can combine them to make fewer equations with fewer unknowns, which usually makes it easier for solvers, but this is how I'm listing it out. So we have 5 equations. So if we have 5 equations, what are our 5 unknowns?
V.
Someone said V, I think. Like the velocity. What else?
D.
D, the diameter, what we're ultimately looking for. What else?
F.
F. What else?
Delta P loss.
delta P loss. And what else? It's one more.
Reynolds.
Reynolds. Okay. So this one, there. Okay, so as I said, you can combine them together, but as long as you can list out equations and you know you have enough equations for all these unknowns, you know that you have the right amount of equations and relationships in order to solve this problem. So the answer of how you would deal with not assuming this V2 is 0 is just, it's one of your unknowns in your system of equations, that's all.
Dr. Nickerson?
Yes, Connor?
So could you explain why the pressure difference then isn't 14 PSI?
Okay, so the overall pressure difference, what we call delta P in the mechanical energy balance, that is, well, technically that's negative 14 PSI because we're going from P atmosphere plus 14 PSI up here to there. So this delta P will be negative 14 PSI. That is the overall pressure difference over this whole balance we're doing. Okay, and then the pressure loss, the pressure drop across the tube is a different, that is different. That is just the pressure loss from right there to right there. It does not include that 14 PSI. It is just the pressure loss to friction.
And so when it says pressurized to 14 PSI of atmospheric pressure, that's saying at the bottom of the tank, it's 14 PSI greater than 0.2. It's not saying at the top of the tank.
We assume the entire tank is about the same. We're going to assume that the height difference inside our tank, well, it's going in, we'll assume that the height difference across our tank doesn't really make that much of a difference. And this, okay, though I suppose depending how big the tank is, you actually could get some amount, but so I suppose if it was like this with, 10 feet of milk, and then it was P atmosphere plus 14 PSI above it, that 10 feet of milk would make a significant difference. But from the way the question is worded, we will assume that is the pressure going in right there. Anyway, and frankly, it probably isn't like that. It's probably filled all the way up. They're really jamming it in there. Okay. And then at the bottom, we say it's atmospheric pressure because that's where it opens up into the atmosphere to go into those jugs. So you would do this. And as I said before, I gave you an example of a solver where you're trying to find the flow rate. I did not give you an example of a solver where you're trying to find the diameter on purpose because I want you to try to make a solver just by yourself without an exact example to follow.
I have a question about this problem.
Brooklyn, and then someone else said something. Brooklyn?
I was just looking, when I did this yesterday, I found the epsilon in the book and it said that it was 0 for plastic. And there was a table underneath that said like, oh, when your epsilon over diameter equals 0, then you can assume just a specific friction factor. I think it was like 0.019 or something.
Well, I doubt it said that exactly.
Or it said like it's approximately equal to that or something along those lines.
So when the epsilon over diameter goes to 0, which it will do here, you're right, because this is plastic, and we generally assume plastic is smooth and you can use 0. Some places you'll find just a very small friction factor or a very small roughness factor for plastic. But again, so if we put it at 0, that's making an assumption. What I think you are talking about is that it says it reduces to, let's see.
Oh, Zach just put it in the chat that it's only good for if the Reynolds number is above a value of 10 to the 6th.
All right, so that is true, is that it's just like with the drag coefficients. If your Reynolds number gets big enough, then it's generally going to kind of even out to some steady number, okay? And it would probably do that for all kinds of materials, but it's easiest just to tell you what it would do for smooth ones. So it's just like those drag coefficients. At high enough Reynolds number, it will basically be constant, but there will be a lot of situations where it won't be.
Okay, thank you.
And then Dr. Nickerson, I had a quick question. And sorry, I think you said this before, but I missed it.
Sorry, just first someone asked a question in the chat. Are we assuming V2 is equal to V average in the system of equations? Emily asked. Yes, in all of these, in these kinds of problems, we always use V average for V. V is V average in here. Yes, Sarah?
Yeah, sorry, I think you said this before, but can you explain why, again, we're assuming that V1 is 0 and then like V2 is not the same?
So V1 is 0 because we're setting we're setting 0.1 here in the tank. And in the tank, where P1 is P atmosphere with 14 psi, P1 is 14 psi gauge, right? And so in the tank is very wide. Velocity will be about 0.
Okay.
And it's sort of that pressure is going to turn into the kinetic energy as it pushes it through the tube. Whereas down here at the bottom, we're doing it right as it comes out.
Okay.
However, and we always use V average for this. The alpha is sort of takes care of the fact that it's V average and actually velocity is changing across the tube. That's what alpha is for. However, as we said at the beginning, in this case, if you assumed V2 was about 0, you'd get about the same answer. It's because this kinetic energy term is pretty small.
Okay. Thank you. So in other words, it's probably best not to like think of like 0.1 as like right at like the entrance of like maybe a little bit further away.
That would be better just because you want to do it when it has that entire 14 psi and none of that's been turned into kinetic energy.
Okay. And then it's also correct if we like assume that like, the velocities are the same as like for 0.1 and 0.2. We would get a very similar
Basically
range.
correct. So not assuming that is probably a little more accurate, but I believe someone said it made a difference of about 0.03 meters in the diameter they found at the end, and or 0.03 inches even. That's even smaller. 0.03 inches is just not significant. Like it's probably there's probably other assumptions in there that are make a bigger difference than that. You can't order a pipe that's 0.03 inches different from another pipe. They don't do that, right? So it would just make the tiny, tiny difference.
Okay, thanks for explaining that again.